Come here, let me show you something. You ready to power up the boat for the first time?
Feels scared. What if it says boof?
It won't go poof. Okay, get in there. And do you see the top left one?
So this one?
Yep, just flip it on. Go
Are
ahead.
you sure?
Yeah, go ahead. For the record, that explosion wasn't real, and the smoke stayed inside the wires as planned. But the $200,000 quote I originally got to wire up our boat very much was real, and that was just for the labor to do the base stuff. And of that quote, about $9,000 was just for the cable to run to the engine rooms for the electric propulsion, which is why I designed our bus bar in the first place. I wanted to show you a little bit about how the bus bar was constructed. If you haven't seen our video where we made our bus bar, or just don't remember, here's a quick recap. Just over a year ago, I had to figure out how to move 50 kilowatts of power around the boat. From the batteries, to the electric motors, to everything else. That is a serious amount of juice. And to carry it through conventional wire, well, you'd need the equivalent of 500 millimeters squared of wire. So it ends up to be like a cable of wire like this size.
Wow. And heavy, right?
It's heavy, and when I ran the cost, it was $9,000 just for the wire. So I came up with an alternative. And that alternative was a bus bar. Cheaper than cabling, smaller footprint, a little bit lighter, but a week of painstaking work to build from scratch. But the only question left was whether my calculations were actually correct. But first, bear with me on this technical bit, because it matters when we get to the test. Basically, it is a pre-made, prefabricated channel that is meant for high voltage industrial applications. So it's 80 millimeters wide on the inside, and the channel is composed of FR4. The channel itself is rated to 5 kV or 5,000 volts, and the bus bar happens to be 80 millimeters wide, and it's 6.3 millimeters thick. So it's actually fabricated for this particular type of bus bar. So if you notice in the little schematic I have here, the negative part is laid along the bottom. And then we have on either side, we have 4 millimeters of the same type of glass. It's a specific type of fiberglass that is very high insulation. So we'll have the positive, and then we'll have an insulator in between, and then the negative, and then in the center there is an air gap. So the air gap is meant for two purposes. One, I wanted to have a little bit of heat dissipation relief just in case it warmed up. And the second is if we happen to get any sort of condensation from having cold air in the bus bar when it warms up, I wanted to have a channel of egress for any water or condensation that might form inside. So the ends of the bus bar are left open, both at the forward and in both engine rooms. So that channel, any condensation will just go to the bottom, and then it will run out. And since we're using tinned copper, it's very corrosion resistant and good for conduction as well. So on top of that, we have 2 millimeters of FR4 glass, and a 2 millimeter layer of that by itself is rated at 1.5 kV. So it's extremely high insulation value. And so I feel very confident that the arcing between the two is not even something to consider. Then on top of that, we have the positive bus bar, and then we have another 2 mil layer of the same type of glass, and then the top of it is sealed. So I think it's a pretty cool design, and today we are going to Well, I got a new piece of gear in the mail. Check it out.
Dun,
It is the Megger. So Megger is basically a very high resistance measuring ohm meter, specifically for testing insulation at higher DC voltages. And this is what I'm using to verify and test the bus bar. You can set voltage settings of 100 volts, 250 volts, 500 and 1000 volts. And since even the thinnest layer of glass we have is rated to 1.5 kilovolts, I don't expect any issues at all. But so now we're testing, we're showing infinity. And then if I place this along the deck, you can see that we have 0 ohms, which is short, which is what we don't want. So I'm going to turn this test off. I'm going to hook it up to the bus bar inside. So that is on the positive side, and then the negative side will just pick up here. And I did make sure that all equipment was unplugged from the bus bar, including the Victron Smart Shunt, because it's not rated for the high voltage that we're going to be testing on, and I wouldn't want to damage any of that equipment. We're going to be on our 1000 volt setting. We're set at the 200 mega ohm range. The Megger works like this. You push a high voltage through a conductor, and then you measure if there's any leakage to the other conductor through the insulation. The number it gives you is in mega ohms, a very high measure of resistance. The higher, the better. I need to run 3 of these tests, from positive to negative, positive to the hole, and then negative to the hole. All 3 should be completely insulated from each other to pass. And we are getting a complete open. Let's go to the 2000 mega ohm range. Now we're starting to get something. Huge amount of resistance. Let's try it at 250 volts. So we're at about 600, 700. That's looking pretty good. Let's go all the way up to 1000 volts. Boom. All right, so I did all 3 tests. They all passed very high readings, around 600 mega ohms, 600 to 700 mega ohms, depending on which one I was doing, at 1000 volts, which is a very high resistance value. Next, I want to do a continuity test. So we did kind of one when Connor was here, but it was using the other meter, and we had some loose connections, and we were using that wire that wrapped around the boat. So I want to redo that. The idea is to actually put some current through the system. There's a tool called a ductor, which will actually run 10 amps of current through a copper loop. Based on the voltage drop, you can get a very accurate resistance value. They're actually quite expensive, so I'm renting one here in Brisbane, but as soon as I get that, I'll do the test on that. And yeah, so far so good. Exactly what I was hoping for. I was a happy guy. All 3 tests were well above anything I needed. But there was really only one thing left to do, and a moment this big needed a witness. So I went and got Kaz.
Okay, well, what's exciting here, Brian?
Well, we're about to do a major test. For the first time, we're gonna hook up the batteries, through all the switches, test the contactors, and then we're gonna go voltage on our distribution side. And everything's been double checked, triple checked. And do you wanna do the honors?
I feel scared. What if it says boof?
It won't go poof. Okay, get in there. Do you see the top left one? Just go ahead and flip that to on. Go ahead.
Are you sure?
Yeah, go ahead.
Oh god.
Tunk. And you actually only turned on battery bank number 1, but that's the master bank. So like bank number 1 kind of like turns on the contactors, powers up the system. So either of those banks can come online, and then it brings the whole system and the network up. And oh look, the Victron Smart Shunt is blinking. Yes, we're connected. Delos 2 house, 100% charge, 53.2 volts, no current flowing because nothing's hooked up. Whew, that's a huge amount of work done.
Wow.
Yes. What we're seeing is voltage from bank number 1.
Yeah.
And if we really wanted to, we could turn on banks 2, 3, 4, like the other 5 banks, just by flipping the switches, and then they would all be connected to the backbone in the whole system.
When all of that is done, what does that mean? That you can actually start like testing winches?
Yeah, so I can start powering up like the DC to DC converters for the 12-volt system.
Okay.
We can put power to the digital switching system and the NMEA network, and start testing like the windlass and the Selden winches, and like everything can start coming online now.
We know this from Sweden. We bought a brand new oven, and after, it didn't work right off the shelf.
Yeah.
And I think it's been really interesting because I've needed to buy stuff like a year ago, and obviously that's not under warranty anymore.
Yeah, we can start testing as we go now.
You've spent a lot of time in this hole here.
I have. But it's all paying off.
Yeah.
We got power now. It might be beer o'clock for me. I'm hot, sweaty, and tired. Oh, and there's so many midgies out. Oh my God.
Many.
Oh, we're probably backlit a lot.
Go this way.
There, that's so much better. Good morning, Bill.
Look at those handsome men.
You embarrassed me.
You make me blush.
Had the little power test with Kaza last night.
Okay.
That went well, so the next step is to bring the N2K network up. So I actually have a list of all the devices that are going to connect here to the N2K network, and it's substantial. So we've got the nav computer. There's actually 2 nav computers. I'm going to be running dual Raspberry Pis, one for the electric motor system and another one purely for navigation and OpenCPN.
Sweet.
The stereo connects so that you can control it through the chart plotter if you want.
Muy importante.
The VHF connects so that you have AIS. The Victron Servo connects so that all of the other information from everything on the N2K network gets pulled into the power system. The autopilot control, definitely, that connects. Bluetooth receiver for the autopilot. We have 3 MFD displays, B&G Triton 2s. We have the B&G Compass for autopilot navigation. We have the B&G Triton sailing computer, which ties all the information and processes it together. We have the B&G converter for the anemometer at the top of the mast. We have the big B&G chart plotter. It's going to sit over here. And then we have all of the digital switching buttons, which also run on the N2K network. So it's a total of about 19, 20 devices.
Yikes.
So it's a lot to connect to.
So a few videos ago, we started on the layout of all the electronics of the helm station. And as we speak, the vertical veneered faces are being fabricated in Steve's shop. So that's happening right now. And timeline-wise, it makes a lot of sense for Brian and Bill to kind of finalize all the electrical stuff that is happening in this helm station, because it's a lot, and for that to be kind of finalized before these panels come back and getting permanently installed. So that's what they're gonna start on right now.
This is the power tee. So this is a Meritron power tee. I really like the Meritron gear for building out networks. I found it very high quality. I used it on Delos 1. This is for the I've used the micro C cable, which will give you a total network length of up to 100 meters, which is plenty for our uses. And if you use an adapter like this, you're allowed to have 4 amps of current on either side, so a total of 8 amps. So what we're going to do is we're going to balance the LENs, they call it. For example, we wouldn't want to put this at one end of the network and have all the devices on one side. We're going to try and put this in the middle so that we can provide power equally to both sides of the network. So this will be here, and then what we're going to do is we're going to build the N2K backbone out from that. We have a bunch of these 4-to-1 splitters, and then we can actually start testing. Like, it's kind of like you build the base system and then you move up to the next one, test it, and then you keep on going up in the stack. You have to task?
Yes.
Yes, you accept the mission?
Yes, I choose to accept the mission.
Maybe we'll put 10 here and 10 there.
Just try to balance it, because you know it's almost 20.
Yeah, 4, 8, 10 on that side, and then we can use this to connect to the other side, sort of like, so that gives us 20 taps right there. You're allowed up to 50 devices on one backbone. And the total network length, I think, is going to be about 70 meters. So it'll go from forward through here. This will be the center of the network. It'll run down that conduit through the port engine room. And then there's a conduit running to the starboard engine room. And it'll come up through a conduit over this side of the boat, through that conduit, and then finish on the back. So it's pretty much a loop around the entire boat, terminating in the bows.
Yeah, so these guys are just in the middle.
Yes.
The middle
exactly,
of the network, basically. And then...
So we should be very close on our balancing.
Okay, so where do we start here, Brian?
Well, I think that the equipment is going to be pretty balanced to either side. And so when you mount these, do you want to mount them like that? Or do you want to mount them like that? Because if you mount them like that, then the cables from the top have to come in and do a loop like that. If you mount it like that, these cables are very convenient. The stuff mounted down here has to do the opposite, right? I was almost thinking, what if we mounted it like that? The inconvenience is that we have to build a bracket. Because the helm station panels are being built at Steve's shop right now, I've only got a narrow window to get all of this wiring sorted before they go in permanently. So my plan is to fabricate a simple aluminum bracket to mount all the 4-way T's in one place. It'll be neat, accessible, and out of the way. See if that fits under there. I think that'll be perfect, right? Be nice and up out of the way.
Yep. Then you think drill a hole for the power cable to go through?
I can drill a hole for the power cable and I can tack this piece right up there. Okay, sweet. It fits, which means the concept works. Time to make it permanent. All this stuff I think should be hardwired to the network instead of via digital switching, because it's like the base of the core of everything, right? So when I turn the batteries on, I pretty much want the MIA 2000 network to come up without exceptions, because that's what brings all the other systems up online, right?
Yeah.
So there should be no off button for it. Wait a second. Are you ready to be wowed and amazed?
Oh yeah, I'm so ready to be wowed.
Are you ready?
Check it out.
Boop.
No way.
Check it out.
Boop.
That's
Pretty
awesome.
cool, huh? To have
Very
lights
well.
on a boat, what a novel concept. And they're dual color, so if you don't want to mess up your night vision, you can go amber. Stuff's starting to come online, Kaz.
Yeah.
Check this out. So this is our nifty little N2K meter, and we're getting a bus power of 13 volts. It has a smiley face if it's good,
Okay.
and if it's not good, it has a frowny face.
Oh really?
So we have 13 volts here. There's a lot of things on this, but what we're basically going to be looking at is bus traffic. So this is actually looking at the sentences that the devices on the network are putting out. And right now there's probably only the batteries and the other transducer, the other depth, speed, temp transducer on the other side. So we're hovering around 1.9 is the highest as a percentage of how much bus traffic the network can handle. So
Okay.
as we add more and more devices like GPS and autopilot, that number will creep up and up and
Like
up.
when everything goes into the nav station, for example.
Exactly.
Yeah.
Anything that's talking. A lot of those things are just listening. For example, all the displays, they mostly just listen for other information. It's the transducers, the GPS, things like that transmit. The chart plotters will transmit. But this is great. We can look at bus errors. So we have 0% per second, 0 per second bus error, big smiley face on that. So this is kind of proving our network design. So now what I'll do is I'll take this meter and I'll go test it on the other end of the network. I'll go test it in the middle at the helm. I'll go test it in the engine rooms, but I expect it to be good.
Yeah.
So that's it.
Cool.
All right, happy times.
Woohoo!